Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.2.7, dot product and the generalized Pythagorean theorem. So let's talk about the pairing idea that we have when we compute a determinant. In the last section, we gave an example of where we have the base in green and then the input in red, if we're thinking of our base input analogy for computing determinant volume. And notice how the green moves up and down, the red moves up and down. Now, wherever the green is, there's a red portion that's associated with it. We take the determinant of this times the determinant of that. This is like a pairing between the left side and the right side. So this paired with that, determinant of this paired with that, and so forth. So we multiply, 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 multiply in all these places, and then we add. We call that a dot product when we take lots of products like that are corresponding and we add them. Okay, so for instance, if we're looking at here, this gives an example of these multiplied together and then added. Of course, we modify the sign by the permutation associated with the pairing, the particular pair of things we're multiplying. And we can use this symbol. So this is a bolded dot here, at least in the text. We have 2, 4, 5 is the input. And notice that the base, now that doesn't look like anything we see here, except it's the determinants. So 4 is paired with 2, negative 12 with another negative with it is paired with 4. So be positive 12, notice that. So 12 will be paired with 4. Negative 16 will be paired with 5, because that's the determinant of this piece, and then put a plus here. So we can kind of think of a pairing idea. So that times that, plus that times that, plus that times that. So this guy right here, the base pairing, happened from determinants. In fact, even in the case where we have like this 5 by 5, the pairing is, a green determinant with a red determinant, a green determinant with a red determinant. Even with the input right here of being just a single vector, really of a 1 by 1 matrix, 2 is its own determinant. So really thinking about determinants paired with determinants here as we make this calculation. All right, notice that if any of the columns repeat in the so this, we'll just remember what this calculation is. This is the calculation for the full determinant, right? Now remember, when we had a determinant where we repeated a column, then it would be 0. So let's say we have 1, 5, 4 here, and let's suppose that we replace this 2, 4, 5 here with 1, 5, 4. Now the pairing from the green will look the same, 4, positive 12, negative 16, but here we'll have a different input, 1, 4, 5, and that's represented right here, 1, 4, 5 paired with the same determinants. So this dot product should yield 0, actually. So the full determinant is 0. Now let's think about that analogously to volume for a minute. So we have base and we have an input coming off of it, but we get 0 volume. That must mean that this, let's see, right. That must mean that the input right here happened to be parallel to the base itself. Now, but what about this right here? This isn't parallel to, meaning the vectors inside of the base, right? But there's a question. What about this guy? So this guy dotted with something that's parallel with the base is 0. But if you have something outside of it, I mean, like if it's even orthogonal or meaning perpendicular to the base and you dot it with this, you definitely won't get 0. You get a nice volume. This dot product must mean that, so this guy right here must, if we're thinking about it that way, oh yeah, let's think about that. The base, like this is a vector. So this is a vector of determinants, right? But this vector of determinants, which direction is it facing? Where is it going? I mean, is it, so let's think about that for a minute. All right. So what if we Okay, this just shows how symmetric this is if we switch the idea of input and base, which we can, by switching this around. We can kind of, by which side we're thinking of input and base, we can do that and kind of rearrange it. We get a zero pairing. Well, why don't we try this? Let's take 154, and let's add it to 245 in the original matrix here that we're working with. All right, so we just add it as well. The determinant won't change, right? The determinant doesn't change. So remember that. Also, okay, now let's put 412 negative 16 in. Now remember what that is. That's the vector of determinants. So let's put that in there. And we'll have a pairing, but the pairing will be basically, look, 4 with itself, 12 with itself, negative 16 with itself. Now that's going to be a sum of squares, definitely non-zero. You don't get 0. However, if you put anything that is a multiple of 154 or a multiple of 3 negative 0, you will get 0. Let's think about this for a minute. Actually, every single thing that you put in for input is the sum, or is in the span of these 3 vectors. 1, 5, 4, and 3, negative 1, 0 actually have, they're not tag-alongs of each other. They actually have a dimension of 2 together. And if you put this guy together, it's actually a dimension of 3 fully. And so actually 2, 4, 5 can be written as a multiple of this, plus a multiple of that, plus a multiple of that. Now, well, what if you do some sliding? Well, sliding by multiples of 1, 5, 4, and 3, negative 0 should not change the determinant. Why don't we slide so that these multiples just vanish? They go away. So basically, the determinant is always the same as just taking some multiple of 4, 12, negative 16 here in this. This is the vector of determinants. So by modifying z, right, we can change, so all we have to do is just change this z value, where this z value represented how we could decompose 2, 4, 5 as the sum of these guys. It was a multiple of that in that decomposition. And then we'd be able to figure out that determinant. Okay, notice, so that's the only thing that really matters is what that is. Now, what if we thought of this as a vector and made it a unit vector by dividing by its length in 3 space? That's like by the Pythagorean theorem, like square root of 4 squared plus 12 squared plus 16 squared. It works the same way in 3 space, but you just have another part to it. So that would give you the length of that vector. What if you divide that by that? So this would be like a vector of length 1. So a vector of length 1, and notice that the volume from base to here only really depends on this part, meaning, and really by sliding, so this is actually rectangular the way we slid it. This is actually what you'd call perpendicular to the base or orthogonal, this particular direction. And you actually can get volume out of this, or actually area even, because if you consider, and let's actually draw this out. So if you consider a base, okay, so you have a base and you have a vector coming out of it that's orthogonal, or meaning perpendicular, and it's of length 1, and you find the volume of this rectangle, it's actually equal to the area, because you're just multiplying by 1 really for height. So this is kind of nice. So we actually can get area out of this, area of the base, by finagling this and making this length 1. And notice it's just by taking the vector of determinants, dividing it by its length. And then dotting it to itself. Let's see, just like this. So this becomes the input, and the base, that should give you the volume. Now notice in this calculation is kind of interesting, because these dot together give you a sum of squares divided by the square root of the sum of squares. This just becomes a square root of the sum of squares. You know what 4, 12, and 16 are? Those are determinants. Do you know what those determinants represent? They represent, let's look back here. They represent projections. projection onto a plane. This is the YZ plane or the ZX plane, or a projection onto the XY plane. So you take a parallelogram and it projects different ways into different planes, and those terms are actually areas. You take the aerial projection into the different planes. You take the sum of the squares and you square root. It's a generalization of the Pythagorean theorem. Instead of projecting lengths onto axes, you project orthogonal or perpendicular axes. You project areas onto there, and then take the sum of the squares, like this. So here's an example. What if we have in 4 space, 4 dimensions, however that would be visualized, but let's project it into different, but let's say have you say 2 vectors, and it creates a parallelogram in 4 space, and it projects differently onto different planes. So there are 6 different 2x2 submatrices, so 6 different projections. Find the areas of each projection, take the sum of the squares, and square root it, and you actually get the area of that parallelogram. It's kind of an interesting idea. Generalized Pythagorean theorem. Thanks for watching.